Dear students, after studying this module, you shall be able to know various possibilities in electrophilic aromatic substitution of substituted benzenes, learn about ortho, para, meta and ipso-substitutions, familiarize with groups that either direct ortho-para substitution or are meta-directing. Acquire an understanding of the observed orientation of the electrophilic aromatic substituted products in benzene and other ring systems. Now students, let us introduce you to this topic. When substituted benzenes undergo electrophilic substitution reactions, then there are usually three possibilities, that is, the substitution may occur either at ortho, para or meta position to the original substituent attached to the benzene ring. Also, sometimes a fourth type of substitution pattern may be encountered, that is ipso-substitution. A special case of electrophilic aromatic substitution where the leaving group is not hydrogen but the original substituent itself. There are four possibilities and these are illustrated in the figure that you can see, either the ortho, para or the meta attack depending on the R group, that is the original substituent on the benzene ring, or the ipso substituent, that means the electrophile comes in place of the original substituent. For example, we can consider the nitration reaction. Now first one is the toluene, second one is the nitrobenzene itself. Let us consider the nitration of both these substituted benzenes. If you see, then the nitration of toluene gives you ortho and meta nitrotoluenes. However, the nitration of nitrobenzene gives you only meta-dinitrobenzene. Now, as can be seen here, toluene has given a mixture of ortho and para substituted nitro products, while nitrobenzene gives meta-dinitrobenzene. The rate of the latter reaction is very slow as compared to the former one. As natural question arises, why? What are the influences of the original substituent in aromatic ring which leads to some observation of these product ratios, and also why such ratios? The answers to this can be found out by studying the electronic nature of the substituent and its effect on the aromatic ring. Now as you can see students, toluene has given a mixture of ortho and para substituted products, while nitrobenzene gives you meta-dinitrobenzene, predominantly the meta substituted product that is. The rate of the latter reaction is very slow as compared to the former one. Now a natural question arises, why? And another one is that what are the influences of the original substituents on the aromatic ring which leads to such observed product ratios? Well, the answers to this question can be found out by studying the electronic nature of the substituent and its effects on the aromatic ring. And in this module, we shall in detail discuss about what affects the formation of these products and as well as their ratios. Now, let us begin with the electronic effects of substituents on the aromatic ring. Based on the observed pattern of electrophilic aromatic substitutions of a wide range of mono-substituted benzenes, that is R(C6H5) as its molecular formula, the substituent R falls into the following categories. First we have the O-NR2, that is the amines, primary, secondary and tertiary amines, the hydroxyl, the OR group, that is the ether group, that is the NHCOR group, and another one is OCOR group. Next category would be NO2, CN, cyanide, sulfonic acid, aldehyde, CHO, the ketones, the carboxylic acids and the amides. Next category students is the salts of the amines, that is NR3+, NH3+, that is the ammonium ion or the trialkyl ammonium ion, CCl3CF3. Next category is alkyl and phenyl. Another one is CO2 minus. Last category is the halogens, that is fluorine, chlorine, bromine and argon. These are now discussed one by one. Now let us come to the first category of the R group, where R, or say X, is equal to O minus Nr2 NHR, that is a primary, secondary and tertiary amine, NH2 also, hydroxyl OH, ether OR, NHCOR, that is the substituted amines, and the OCOR groups, that is the ester groups. These group, with an exception of O minus, show an electron withdrawing inductive effect. We also call it as minus I effect, as the atom directly attached to the benzene ring is more electronegative than the carbon to which it is attached, that is the sp2 carbon of the benzene ring. On the other hand, students, there is also a strong plus R effect, that is the resonance effect, since each of these groups has a lone pair of electrons which they are able to donate to the ring via resonance. Now you can see this over here, how the donation of electrons is taking place. Now we can see the effect also, how the effects are changing with each and every single group, that is X. Thus, these groups make the ring more electron rich than the original benzene ring, and hence making the ring more susceptible to attack by electrophiles. Thus, aromatic rings bearing these groups react faster than benzene, and the groups are said to be ring activating. O minus is greater than the tertiary amine, that is the Nr2, then the secondary amine NHR, then the primary amine NH2, followed by hydroxyl, ether and the substituted amine NHCOR, followed by the ester. The latter two are less reactive or the less activating than the others, because the lone pairs on the heteroatom are to some extent also being delocalized onto the carbonyl group which is present. Now, to explain the orientation in these cases, as can be seen from the preceding figure, the resonance effect builds up in negative charge only on the ortho and the para positions in the starting material. Thus, one can expect the electrophile to attack these positions selectively. Also, if one may consider the formation and stabilization of the VLAN complexes or the arenium ion or the so-called sigma complexes of the three possible modes of electrophilic attack, the same conclusion shall be reached. The same is explained as in the case of anisole, and you can see here, consider the ortho attack in this. Now, since the oxygen is more electronegative than the carbon it is attached of the benzene ring, now you can see it is going to increase the electron density only at the ortho and para positions. That means it is going to facilitate the attack of the incoming electrophile at that position. And also, if you see the resonance forms in the meta attack, then you can see the positive charges are generated at the ortho and para positions. As illustrated for the attack of either ortho or to the para positions, the VLAN intermediate has an extra canonical form in which the positive charge is delocalized onto the oxygen atom. Now you can see, as I told you, this positive charge is being delocalized on the oxygen atom by the involvement of the lone pair on the oxygen. This is not possible attack on the meta position, and hence the meta attack intermediate is less stable because it has less canonical forms than those from either the ortho or the para positions. However, students, it might be noted that steric effects also come to play, and hence the ratio of the ortho and para products is approximately 1:2 for anisole, because this ortho position, students, is very much close to the actual substituent, that is the anisole OCH3 ether position. Because steric hindrance is counting a lot here, that means that shows that the para position will be much more favored, and because the meta position only has less canonical forms than the ortho and para, it is formed in the least percentage, followed by the ortho one, and next the para one, it is formed in 67%. The ortho product is formed in 31% of yield. Now, we can conclude that these following groups that I have stated just now are activating and are clearly ortho and para directing. Let us come down to the second category of groups. They are R or X is equal to NO2, that is nitro, cyano group CN, the sulfonic acid SO3H, the CHO aldehyde, COR ketones COOH, that is the carboxylic acid, and the amide CONH2. These groups show a moderate to strong electron withdrawing inductive effect, that is the -I effect, as these possess a partial to full positive charge on the atom directly attached to the aromatic ring. They also display electron withdrawing resonance effects, that is -R effect. Now, you can notice, students, here, although the groups that we have discussed above in the first category, they were also having the heteroatoms whose electronegativity was more than the carbon which is attached to the benzene ring. Here also it is the same case. However, these groups specifically display electron withdrawing resonance effects, thus -R effect is seen here as compared to the earlier category where +R effect was seen. These effects are illustrated in the case we have taken here, nitrobenzene. Now, you can see the nitro group is actually pulling the electron density from the benzene ring towards its own oxygen atoms. As oxygen is obviously more electronegative than nitrogen, thus the electronegativity comes more onto the oxygen atoms, right, being pulled away from the aromatic ring. In effect, they make the aromatic ring electron poor in comparison to benzene and thereby act as strongly deactivating groups. That is, reactions proceed much slower in rings bearing these groups compared to original benzene rings. Also, the orientation of the resulting product can be predicted in two ways in presence of these groups. Presence of positive charges at the ortho and para positions in the resonance hybrids as shown above from nitrobenzene will dissuade the electrophile to attack these positions because they are already bearing positive charges. Hence, meta product will be mainly predominant as only the meta position now is available for the electrophile to attack. Second is by comparing the stability of the VLAN intermediates. Now, you can see, if you see the stability of the VLAN intermediates in the ortho attack, here you can see the positive charge is on the carbon which is next to the nitrogen, thus making it unstable in case of ortho attack. In case of meta attack, there is no such positive charge on the carbon which is directly attached to the nitrogen of the nitro group. Thus, it is relatively stable. However, again in case of para attack, students, note that the positive charge is on the carbon which is directly attached to the NO2 group. Thus, again an unstable VLAN intermediate occurs in the case of para attack, just as in case of ortho attack. Now, as shown, while attack at the ortho and para position will lead to one canonical form wherein you can see again a positive charge is situated adjacent to the positively charged substituent, which is unfavorable electrostatically. Thus, in such a situation is avoided, that means ortho and para attacks are avoided, thus meta attack is favored. Hence, these groups are called deactivating and meta directing. Now, students, we will summarize the two groups we have studied till now. First was activating and ortho-para directing. The second category is deactivating and meta-directing. Let us come down to the third category, that is where R or X is equal to Nr3+, that is the salt of the amines, or the ammonium ion NH3+, the trihalocarbon, that is CCl3 or CF3. These groups also show a strong electron withdrawing inductive effect, that is the -I effect, due to their positive charge or because of the strong electronegativity of the halogens or the heteroatoms which are attached to carbon, which leads to a positive polarization of the atom directly attached to the aromatic ring. However, there is no resonance effect as there are no orbitals or electron pairs which can overlap with those present in the ring. The inductive effect creates small positive charges on the ortho and para positions, but not on the meta position, and it destabilizes the VLAN intermediate which is involved. Hence, these groups are also deactivating and meta directing. Now, as you can see here, the charges in the benzene ring, that is the electron density in the benzene ring using these groups, is basically being pulled towards the nitrogen atom carrying the positive charge, and thus there is a positive charge on ortho and para position of the aromatic ring. However, there is no positive charge on the comparatively on the meta position, thus they are meta directing. So, for the deactivating meta directing groups discussed here, the effect in the decreasing order will be, now you can see here what will be the effect in the decreasing order. You will have first the Nr3+, that is with the N and the positive charge, then the nitro, then the cyano, then the sulfonic acid. Note that cyano and sulfonic acid are almost at the same position, almost have the same electron withdrawing effect or the deactivating effect. Then comes the phenyl ring which is attached to the aldehyde. Then comes approximately similar one is the ketone. Then comes your carboxylic acid, and similar position is held by the CCl3 group or CF3 group. Next category students is the alkyl or the phenyl groups. Since there is a weak electronegativity difference between the carbon of the alkyl group and the hydrogen atoms, the carbon atom becomes more electron rich and it passes this electronic current to the aromatic ring. Thus, there is a weak inductive effect, that is a +I effect. Also, weak resonance effects arises from hyperconjugation, also taught to you as no bond resonance, which also increases the electron density in the ring. Now, you can see here again the electron density in case of +I or the activating group such as alkyl and phenyl comes at the ortho and para position. These two effects will thus aid the attack of electrophile, albeit very weakly. So, alkyl groups should be mildly activating. So, you can see the difference between the first category and this fourth category is that these are mildly activating. Also, they are weak ortho and para directing groups, and they can be seen by the resonance hybrids of the substrate or by the stabilization of the VLAN intermediates. And you can see here we have shown here for the ortho attack the formation of the VLAN intermediate or the arenium ion which is there, and you can see how in this the ortho attack is favored. Now, in case of a phenyl substituent, resonance stabilization of the VLAN intermediate takes place for ortho and para electrophilic attack, and thus it is a weakly ortho and para directing group. Coming down to the fifth category of groups where R or X is equal to the carboxylate ions or anions, you can say, depicted by CO2 minus. There is almost a zero resonance effect since the negative charge of the anion is itself delocalized with the carbonyl group of the carboxylic acid. So, there is no electron withdrawing resonance effect in case of carboxylate anions. The negatively charged carboxylate ions moderately repels the electrons in the bond attaching it to the ring. Thus, there is a moderate electron donating plus I effect, producing small negative charges on the ortho and para positions. However, there is no charge on the meta position. So, overall students, the carboxylate group has a weak activating influence on the aromatic ring and hence it is ortho and para directing. Similar argument we can apply for the stabilization of the V-line intermediate in this case. Now you can see here how with the carboxylate anion, apart from delocalization on the carbonyl group, how the negative charges partially are being delocalized on ortho and para position, however not on the meta position. Thus students, we can clearly say they are weak ortho and para directing groups, the carboxylate anions. Now the sixth category students and the last category is the fluorine, chlorine, bromine and iodine, that is the halogens, where X is equal to the halogens or the R group is the halogens. Consider the nitration of chlorobenzene. Now you can see here how the products are formed. You can see that the ortho-nitrochlorobenzene is 35% in yield and the meta one is only 1% and the para-nitrochlorobenzene is formed in 64% of yield. The reaction is much slower than benzene and ortho and para products are mainly formed, as you can see already in the figure. To justify these effects, consider the properties of the halogens. These are powerful electron withdrawing elements in the periodic table, that is they are very electronegative and they show a strong minus I effect, thereby deactivating the ring for electrophilic attack. However, the halogens have also the lone pairs of electrons that they can donate via resonance, that is the here plus R effect in these sigma complexes for ortho and para electrophilic attack. While the reaction at the meta position does not allow for the positive charge to be placed next to the halogen and therefore does not result in any stabilization. The canonical forms of the sigma complex for para electrophilic attack, they are definitely shown here and you can see that para is the most stable of all the V-land complexes that you can make here and thus these groups, that is the halogens, are deactivating but they are ortho-para directing. They are, again I would like to reiterate this fact, they are deactivating because they are electronegative atoms, but because of the presence of lone pair they can increase the charge, that is a negative partial negative charge on the ortho and para positions of the benzene ring. Thus the electrophile will be favorably attacking on the ortho and para position only. Thus students, you must take care here that they are deactivating but ortho para directing in nature. Effects of more than one substituent. Now let us come on to discussion about this. The cumulative effects of both substituents have to be taken into account and it is often possible to predict the correct isomer of the electrophilic aromatic substitution, especially when groups on the ring reinforce their directing abilities. For example students, let us see here the metachloroanisole or the carboxylic and the nitro group add meta to each other and the nitroanisole or the meta-methyl nitrobenzene, you can say, consider them as A, B and C. In the molecule A, where both the OMe group, that is the ether group, and the chloro group are ortho and para directing, will cumulatively guide the incoming electrophile to the ortho or para positions as marked in the figure. Similarly, students, if you see in the molecule B, both carboxylic acid group and nitro are meta-directing, and they will guide the incoming electrophile to only one of the meta position as marked in the figure. However, if you look at the molecule C, where the groups oppose each other, that is, one is ortho-para-directing, other is meta-directing, one gets confused and it is very difficult to decide where the incoming electrophile will go, and often a mixture is formed. And then we have to see the strength of each of the groups present and which will favor more and which will favor less. That means the stronger group may be ortho-para directing, then the incoming electrophile will go on the ortho and para positions available. If the stronger group is meta directing, then the incoming electrophile will definitely go on the meta position. However, there are some general rules for prediction of the orientation of the incoming group. We can arrange the groups in order of influence. Now basically we students, we are reiterating the fact that is stated by me. We will have to see which group is stronger. You can see here the O minus NR2 NHR, that is the primary, secondary and tertiary amines, hydroxyl and the ether. They are all stronger than NHCOR, OCOR, greater than the alkyl, greater than the all the halogens coming together, then greater than all the meta-directing groups. Due to the steric reasons, the electrophile is less likely to attack between the two groups. When an ortho-para directing is meta to the meta-directing group, the electrophile goes predominantly ortho to the meta-directing group rather than para to it. Now you can see there is one meta-directing and there is one ortho-para directing, so it will go ortho to it rather than para to it. Now let us come to Ipso-substitution. There is also a possibility of electrophilic attack at the ring carbon atom to which the substituent R or say X is attached. So substitution of the original substituent by the electrophile is termed as Ipso-substitution. Now you can see here that the incoming electrophile E has actually replaced the earlier X group. As can be logically anticipated, Ipso-substitution will be promoted by those substituents, that is X, which can form a stable X plus cation after attack by the electrophile, and they are good leaving groups. Thus, substituents such as bromine, iodine, that is silanes, alkyl silanes, that is SiR3, SN10 alkyls, that is SNR3, and generally alkyl groups, usually secondary and tertiary alkyls, which can form stable carbocations, undergo electrophilic aromatic substitutions, predominantly forming the ipso product. Some examples of ipso substitutions are provided below. Now you can see here in case of silanes how it is a good leaving group and how it leads to the formation of benzene again. Similarly, in case of the second example, you can see here the formation is of the tertiary carbocation, which is very stable. So it forms for a very good leaving group, and the resulting product which is formed is the benzophenone. The third example, students, is the X group, which is the ether group where the X leaves, and then you can see only the nitro group is incoming. Also, proto-desulfonylation occurs where the electrophile H plus replaces the substituents SO3 minus, which subsequently is hydrated to form H2SO4. Now you can see here in this reaction what I have stated. However, the ipso attack can theoretically have 5 possible fates. Electrophile migration is one, ipso group migration is second, ipso group loss is the third one, followed by electrophilic loss, and the fifth one is nucleophile addition. This is shown here, the different fates of ipso substitution. Orientation in other ring system. Now apart from benzene, we have multiple ring systems also. Say naphthalene In naphthalene, there are only two possible sites for substitution. First one is alpha and second one is beta, as is shown here in the figure. All others are equivalent to 1 or 2 or alpha or beta. However, electrophilic substitution predominantly occurs at C1 then C2. This can be explained on the basis of stabilization of the respective sigma complexes. Now you can see here, if we talk about stabilization of the sigma complexes or the Wieland complexes, if the attack is at C1, there is stabilization by allylic resonance or the benzenoid character of other ring, and it is maintained, the benzenoid character. However, if the attack is at C2, the benzenoid character of the other ring is definitely sacrificed for the stabilization of the negative charge by resonance. Similarly, if you consider anthracene, electrophilic substitution occurs at middle ring via intermediate A. This is due to the fact that intermediate A has one resonating structure preserving two benzenoid rings, which is lacking in the other two modes of attack. That means that is favored. For heteroaromatic systems such as pyridine, furan, pyrrole, no generalizations can be made. However, each group has to be studied differently from one. Pyridine, for example, it reacts very slowly towards electrophilic aromatic substitution, and its reactivity resembles that of nitrobenzene, as the presence of a highly electronegative nitrogen atom in the ring causes pi electrons to be held more strongly than in benzene. Now, electrophilic aromatic substitutions take place at position number C3. For example, sulfonation of pyridine at high temperature shows that pyridine sulfonic acid is formed. In case of pyrrole, furan and thiophene, they are relatively reactive towards the electrophilic aromatic substitutions, as a total of 6 pi electrons are present in the delocalized pi orbitals shared between 4 carbons and 1 hetero atom. That means the lone pair is also available in the sharing of the formation of 6 pi electrons. However, this is not the case in pyridine. Thus, these are pi excessive heterocycles and pi electrons are held less strongly. Substitution at C2 is favored over C3. For example, pyrrole undergoes nitration at C2 position. Now you can see here how the C2 position is favored over the C3 position. Now students, it can be clearly seen from above resonating structures for nitration at C2 and C3 respectively that substitution at C2 has more resonating structure and thus is favored position in case of furan, thiophene and pyrrole. Now let us summarize this module students. When substituted benzene compounds undergo electrophilic aromatic substitution reactions, we learned that there are 4 possibilities for the same, that is ortho, meta and para positions to the original substituent, or the Ipso-substitution may also occur. We learned that electron donating substituents like O-, primary, secondary and tertiary amines, hydroxyls, ether, NHCOR, OCOR, that is the ester, are activating and ortho-para directing groups. Electron withdrawing substituents like nitro, cyano, sulfonic acid, aldehydes and the ethers, carboxylic acids and amides are deactivating and meta-directing. And we also learned that the salts of amines, that is Nr3 plus ammonium ions and the tri-halocarbons, that is CCl3, CF3, are also deactivating and meta-directing, as these show strong electron withdrawing effect, that is the -I effect. Alkyl or phenyl groups are mildly deactivating and ortho-para directing due to hyperconjugation and resonance effects respectively. Carboxylate anions, that is CO2-, show weak activating influence on the aromatic ring and are ortho-para directing, and there is moderate electron donating plus I effect. Halogens like fluorine, chlorine, bromine and iodine, all 4 of them being very electronegative, show a strong minus I effect and are thus deactivating. However, we taught you that they are ortho-para-directing by virtue of the lone pair of electrons which they can donate during resonance stabilization of the VLAN intermediates. When 2 substituents are present in the ring, the cumulative effects of both of these substituents have to be taken into account, and it is often possible to predict the correct isomer of electrophilic aromatic substitution when they are reinforcing each other's effects. Substitution of the original substituent by the incoming electrophile is termed as Ipso-substitution and commonly encountered with substituents such as bromine, iodine, silanes and trialkyl tin and the generally alkyl groups, usually secondary or tertiary alkyls because they form stable carbocations and the sulfonic acid. Orientation in other ring systems from benzene, including heteroaromatic systems, can be predicted on similar lines by considering the resonating structures of the sigma complexes or the VLAN intermediates.